Hi friends, very good evening and thank you for joining in. Could you please confirm in the chat window if everything is working as expected so that I know that there are no technical glitches whatsoever. Again, if you're not able to see the chat window, just refresh the page and you'll be able to see it. Is everything all right? Let me also see it on my laptop. Cool, things seem to be good. Yeah, it's working as expected. Good. So let's wait for a few minutes while everyone joins in. We will start the session itself at 7:02 or 7:03. So in the meantime, any questions you have, I'll happily answer those. Number one. Number two, I also understand that there is a very interesting cricket match that some students or some people who would want to watch this session might also want to watch, because I think it's a very important match between India and New Zealand. I completely understand that. That's okay. So we'll try our best to cover as much as possible in this session. Cool. Sounds good. Cool. Since everything is working and no glitches, that's good to know. Very good. Let me just check. So any questions related to this topic that we're discussing, please feel free to post them. I have the chat window right here. I'll try to pick a few questions and answer them. Very nice question from Amriz. So he says, I'm a student of Applied AI course. How to revise the concepts and take notes? I tend to forget very easily. Very nice question, Amriz. So first thing is, this is what we often suggest. Whatever concepts you're learning in a week, at least set aside a couple of hours every week to revise whatever you've learned in that week. And when you're making notes, one mistake that a lot of students commit is, they watch the video, they pause it and start taking some beautiful notes. Please don't do it that way, because it takes up more time. Imagine you're actually in a lecture hall, right? See, all of your college days or school days, right? When an instructor or teacher is teaching something, you take live notes. We strongly recommend you do the same thing even with Applied AI course. While the video is happening, whatever you think is important, because even in the video, we typically write all the details on a blackboard type of setup. So write down the notes as you're watching the video. And at the end of the video, for example, imagine you have spent 2 hours in a day and wrote some notes, etc. At the end of it, quickly go through your notes in about 15 minutes, no more than that, right? So at the end of your learning session every day, you're spending some time revising whatever you've learned in those 1.5 to 2 hours. At the end of the week, you're again revising all of your notes. At any point in your notes, when I say revise, one very important strategy that you can employ is try to derive all the mathematics. Try to think from first principles and arrive at the mathematical formulation if it's a mathematical concept. If it's a coding related concept, try to write that code on your own, right? Or at least try to write pseudocode if not full code. That will give you the confidence. And wherever you're getting stuck, you can always go back to your notes or always go back to the videos. So daily, at the end of whatever you're learning, a quick 10-15 minute revision. At the end of the week, a couple of hours. And at the end of the month, maybe you want to have 1 or 2 completely off days where you're revising everything you learned in the month. Again, in a month, you would also end up doing 1 to 2 assignments. Also, again, assignments are a form of revision in Applied AI course, because whatever you're learning, you apply it and you implement it in code, right? So try to make sure that your assignments are a form of revision for you. This is what a lot of students actually do. So monthly revision, and once every 3 months, try and do a big revision. Maybe you want to block 1 whole week, revise everything that you learned in those 3 weeks. This sort of spaced revision methodology, and again, revising by trying to work out things from first principles, will help you immensely. Again, without the syllabus or the breadth of concepts that you need to learn is quite vast for machine learning and data science careers. So you have to have this spaced revision strategy. Otherwise, everybody will forget it. To be honest with you, I'm very much like you, Amriz, that when I learn a concept, if I don't revise it after a week or after a fortnight or after a month, I tend to forget, right? So imagine if I read a research paper, which I think is important, I actually make a note to revisit. So when I'm reading a research paper, I make my highlighted short notes on it. So I try to revisit that research paper maybe 15 days later or 1 month later to make sure that I understand it and I can apply it to some problems that I'm solving, right? Very simple strategy. It's called spaced revision. Very well known, very well researched topic in education in general. Cool. So what are the best books for advanced, from basic to advanced levels in machine learning? Again, Amit, typically books have this fundamental flaw that I've observed, especially in machine learning, which is that they're either too theoretical or too code oriented. What is required is a blend of both, right? So if you take, let's say, so let's take this pattern recognition book, right, by Christopher Bishop. Very nice theory, very beautifully explained. The mathematics is brilliantly explained. It's a standard textbook at most for most machine learning courses at undergraduate and graduate level. Similarly, if you take Elements of Statistical Learning, right, by Trevor Hasty and others, phenomenal textbook. If you already know some statistics, it's mathematically a little dense, but a phenomenal textbook at graduate level. Similarly, the Deep Learning book by Ian Goodfellow, very nice book. So some of these books cover the theory very well. They don't cover programming and applied aspects as much. On the other hand, you have all of these very nice programming oriented books from people like O'Reilly Media, right? So O'Reilly has all of these hands-on coding related stuff. They cover the code well. They miss out on two aspects, which is they miss out on how to apply the concepts to real world problems, to completely unseen problems, number one. Other aspect that they tend to miss out is the depth of theory. So if you're planning to learn from books, try to mix and match these books. Try and pick some hardcore theory books like Pattern Recognition by Christopher Bishop or Elements of Statistical Learning by the folks at Stanford, Trevor Hasty and others. And try to pick up Deep Learning from Ian Goodfellow and similar books from O'Reilly, which are the best sellers, right? I think there is a book called, there is a book on programming in scikit-learn and TensorFlow, very popular book. That will give you a hands-on coding experience. So this is how you can blend these books and learn if you are the type of guy who want to learn from books. But also learn that most books get outdated very quickly in machine learning. Fundamentally because the technology itself is fast evolving. Like most deep learning books today don't cover transformers and other state-of-the-art technologies in NLP, which have become like so popular that everybody uses them and everybody has been using them for the last year to two. So you also have to have this habit of reading research papers or at least the technical blogs that explain these research papers. If you can mix all these three, technical blogs and research papers, strong theory books, coding books, I think you can blend them and learn through all these three means. Cool. Yes, so Nagsai, this recording will be available on YouTube itself so that you can watch it at a later point of time. That's how all of our public live sessions are. Even in our course videos, we'll add this as an optional topic so that probably at the very beginning, so that students who want to get this high-level view of all the libraries can get it at one place. So this is a question from Roshan about operations research emerging very fast. Again, Roshan, operations research has been there for about a few decades now. There are a lot of universities which even offered master's degrees in operations research. So it's certainly an important topic from a business standpoint. It's always been. It's not that it's evolving something new. Of course, it's applied in supply chain management, other really important business problems. Now, the overlap between operations research and machine learning is in the optimization part. A lot of operations research folks use optimization techniques to solve their problems. The optimization techniques may not be exactly the same as we use in machine learning and deep learning, but those who know operations research, because they have strong foundations in numerical optimization, mathematical optimization, they can pick up machine learning and deep learning. Of course, at the end of the day, these topics overlap quite a lot, especially on the optimization front. Like gradient descent based methods are studied extensively in operations research also. They're also studied in like convex optimization and topics like that. Again, only some of these techniques are used in modern machine learning and deep learning and not all. So operations research has always been there. Again, it has its own applications in e-commerce stocking, how much should you stock, and your supply chain management and problems like that. Very, very relevant problems. Again, for some of those problems nowadays, machine learning and deep learning techniques are also being employed. So is ML being used in blockchain and crypto? This is from Rutvik. Again, Rutvik, I'm not an expert in blockchain and crypto. I know the basics. I've read a few research papers. I've read some code libraries. I've read some implementations. But I see both of these as two driving forces. There are a few applications of ML in crypto, etc., but it's not like they're tightly integrated or they're tightly, they're tightly overlapping. Right? They're two distinct technologies. There might be some overlap, but they have their own applications and their own applicability in general. Cool. So, Vignesh, I'm happy you liked the hypothesis testing video. It's certainly one of those tricky topics in probability or probability or applied statistics that we don't get the very first time. It's slightly tricky. Anyway, so let's get started now. Since it's 7:06, let's get started with today's session. Just give me a second. I'll start sharing my screen and we will get started. Cool. So can you just confirm if my screen is visible? Let me also open everything on my phone just so that I can see your chat while it's happening. Okay. So is my screen visible? I can see it on my own phone, so I'm assuming it should work reasonably well for everyone. Cool. So let's get started with today's session itself. In today's session, we want to give you an overview of all the popular libraries, tools, and technologies that are being used in machine learning and AI as of now. Again, the libraries, tools, and technologies keep evolving over time, right? Again, this is not a dive deep into each of these libraries, but we hope this will give you a big picture view of all the stuff that you could learn or you should learn if you want to build careers in data science and machine learning. And these are also tools that a lot of machine learning and data science teams across the world use. Again, just a few quick pointers here. Please understand that this is in no way an exhaustive list. It is only a list of tools and technologies that we see being used extensively within our own network of friends, colleagues, and people that we work with very closely. And to be very honest, this list of technologies or popular technologies is always evolving. If you asked me this question 3-4 years back, my answer would be slightly different. And probably 2 years from now, these technologies will change. Probably better technologies will come, better libraries will evolve. So this list of popular technologies, tools, and libraries is always evolving and changing over time. So whatever I'm mentioning is as of 2021, these are the most popular tools. Again, this popularity is also based on our own experiences talking to hundreds of data scientists and machine learning scientists across the world, wide spectrum of companies from small startups to FANG-like companies. Again, in many companies and organizations, there will be specific preferences for an organization or a team, right? Let me give you a simple example. Suppose if you have to deploy, let's say, a GBDT-based model, right? A gradient boosted decision tree-based model. So a lot of FANG-like companies have built extremely efficient C++ code, which they typically use because they have built this code trying to optimize it for their specific hardware needs, right? So imagine if a company like, let's say, Facebook or Amazon has invested a lot of time and energy to build a phenomenal C++ library for boosting, right? Very often, most teams in that organization end up using that because it fits better into their ecosystem of hardware and software tools. So there will be some of these org and team specific preferences. There might be some closed source technology also, which is not open source, so which we outside a few organizations may not have access to. And one of the most important things in this session is to help you have an assessment and a sense of what to learn and how much to learn. Because there is so much to learn in terms of libraries and tools. Oftentimes students ask us that I'm overwhelmed with so much to learn, right? How much and how best to learn some of these things. So we will also focus not just on the pure applicative side, but also on the learning front, on what to learn and how deep and how wide you should learn a topic. Okay, so I will be using some of these labels for every concept, library, or tool. Mostly we'll be using tools, technologies, and libraries. I will also mention a label like this. Whenever I say I, it means you have to understand the internal workings of that library or tool or technology. A simple way to know whether you know the internal workings or not is simple. can you implement it from scratch? That's the simplest way to answer. For example, imagine if you have scikit-learn, right? Very, very popular library for classical machine learning algorithms. Again, this is whole a Python library, very beautiful, very well-written library. Now, we say typically that you should, for scikit-learn, we will use a tag I. What it means is, for most functionality that you often use in scikit-learn, you have to understand the internal workings of this library. You have to understand, for example, imagine there is, let's say, logistic regression, right? So if instead of just using the logistic regression function, right, you also have to know how this is working internally. And the best way to assess if you really understand the internals of scikit-learn is, can you implement this functionality yourself from scratch without using this library? That is the best way to test whether you know the internals or not. This is like a good way to test yourself. Second is, you could also have a user level understanding. Instead of internal workings, you could have a high level user understanding. For example, let me give you an example here, right? So let's take Docker, right? Which is a virtualization technology, which is often used by folks in ML Ops. So a lot of software engineers use it. Nowadays, this is also a very popular virtualization tool or a containerization tool that's used by machine learning folks for ML Ops and productionization. Here, you may not have to know the internal workings because you're not a software engineer or a DevOps guy. What is important is you have to understand it at a user level with some high level intuition on what's happening under the hood. You need not know nitty-gritty details, right? Most data science folks need not know how Docker works, the nitty-gritty details, the way a DevOps guy or even a software engineer might know, right? So when I say you have to know at a user level, what it means is you have to understand how to use it. You have to have a decent understanding of the high-level intuition of how it works and underneath the hood. Simple like a block diagram is good enough. So when we say these are the two questions you should ask. Can you use this tool or can you use this library? If so, good. Can you explain what's happening under the hood? Can you explain me how containerization works and how is it different from virtualization at a high level? We are not expecting you to be an expert in operating systems, expert in virtualization and containerization technologies. At least do you know how it works and what are the fundamental reasons why Docker is used in machine learning. Some high-level intuition is good enough, right? So we will use these tags I, U. There are other tags also which we will use. This will help you assess how deep you should know. They'll help you understand the depth of your learning, right? For example, some concepts you should know like the internal workings. For some concepts, just having user level with high level intuition is good enough, right? Similarly, sometimes we'll also say I by U. We'll use this label I by U for some libraries and tools. What it means is, it's preferable if you know the internals, but it's not always a must. Even just having a user level understanding is good enough. Again, when we say, this is I by U basically means it's good to know the internals, but even if you don't know the internals, if you just know the basic user level stuff, that's good enough. Now, one other very important thing here is we recommend for some of these things to learn the internals if you fall in one of these two categories. If you come from a CS or IT background, for example, let me give you a simple example, right? So there is file handling, right? I'll just give you a simple example. There is file handling in Python, right? For most people who do not come from a CS or IT background, you may not know how files work internally in the operating system because you have not studied operating systems as a course at an undergraduate level, right? But if you come from a CS or IT background, it's important and it's helpful to understand how file handling actually is done internally by the operating system because you've studied operating system at an undergraduate level, right? So number one. Number two is if you're thinking of top companies, right? If you're thinking of FANG-like companies, top product-based companies, knowing some of the internals for those topics that we will label as I by U is helpful. Not necessary always, not for all roles, but sometimes it is helpful, right? So these are some of the labels that we will employ. Similarly, there are other labels. For example, if there is a topic or if there is a tool or a library for which if we use the tag G, it means it's good to know, not a must know, right? When I say good to know and not must know, what you should have is the ability to pick up this library or tool or technology if the need arises. You should have the ability to pick up this technology. For example, take the R programming language, right? Slowly lesser number of people are using the R programming language. But there might be one instance in your organization where you have to use the R library because there is some older code that some other team has written that you might have to modify. So this is good to know, not a must to know, but you should have the ability to pick it up if need arises. Similarly, for some topics, we will use the label MLE. This is especially useful if you're planning to transition into ML engineering roles. Again, ML engineers, sometimes also called as software development engineers for machine learning, are people who spend approximately 50% of their time on software development and approximately 50% of their time on data science and machine learning stuff. So if you're looking for machine learning engineering roles, again, this is most optimal for people who come from CS or IT background or who are already software engineers in the industry. Similarly, there will be some topics and libraries where we'll use this label C. It means use a cheat sheet. Use a cheat sheet because let's take a library, right? Let's take a library like NumPy. It has thousands and thousands of functions. Now, very often asked questions that students ask us is, hey, there is so much to learn in NumPy. What should I prioritize? It's simply impossible for me to keep a track of everything in NumPy because nobody remembers NumPy. So two things. So in such instances, we will label this with C, which means use a cheat sheet. You can Google search, you'll get cheat sheets. Cheat sheets help you understand what to prioritize. Again, in a cheat sheet, you might have some 10 or 20 functions or 20 operations that you want to prioritize because these 20 operations are so widely used in the industry. This is especially useful if you have a large library or a complex tool. Cool. So let's go step by step now. So I've just explained what all labels we will use when we label various tools, libraries, and technologies. So let's dive into the actual tools and technologies. First is obviously Python, the core aspects of Python, right? So you should certainly understand inbuilt data structures. Your dictionaries, your sets, your tuples, your lists, you should understand them fairly well. Your arrays, obviously, strings and all of that. So for inbuilt data structures, you have to understand how things work internally. And if you're confused, always use a cheat sheet because sometimes there is so much to learn, right? There will be tens of functions that you can apply on a simple dictionary. Now, which of them should I use? Just do a Google search, you'll get a cheat sheet. Let me show you a simple example, right? So you can just do this and you can say, hey, cheat sheet. Okay, sorry, so let's just use this. So cheat sheet and let's just say Python data structures. Okay, so you'll get a ton of these. Okay, so this is from GitHub. Okay, so look at this. So introduction to arrays, tuples, array sequences. Okay, this is queue. Again, we can limit ourselves just to the inbuilt ones first, and then you can go to the other ones. Okay, data camp. Okay, let's just go here. Okay, so Python this is Pandas cheat sheet. Okay, so if you just Google search, you'll get it for almost any major library or toolkit. So this is from data camp, and this is Python for data science. This is for Pandas. Right? Pandas is another very popular library. So you'll get, okay, how is the Pandas data structure internally? How do you drop something? How do you sort and rank? How do you select? How do you align? How do you apply functions? Input, output. So typically for any large library, if you just Google search and say, hey, Python dictionary, right? So imagine you have a data structure which is dictionary, which is nothing but a hash table in Python. Python dictionary cheat sheet. You'll get a cheat sheet. Again, there might be multiple websites from which you can get cheat sheets. Pick any one of them that works better for you. Any one is good enough. I mean, that's why I'm not specifically recommending one cheat sheet versus others, because no one cheat sheet is perfect for everyone, right? Whenever I need a cheat sheet, I just Google, I look at 3 or 4 of them, whichever I think is most suitable for what I'm doing at that point, I pick it up. So for inbuilt data structures, you have to understand how things work. You have to understand how dictionaries work. What is the time complexity? What is the space complexity, right? Where to use them, where not to use them. Similarly, if you have, let's say, a list, you have to understand what are the advantages and disadvantages of a list, where to use it, where not to use it. How is a list organized internally, right? So you have to understand the inbuilt data structures, the internals of it. This is mandatory for almost all data science and machine learning roles. And the best way to understand or to remember the most important functions, just use a cheat sheet. Similarly, object-oriented programming. This is super duper important because you use it. Maybe most data scientists may not write like object-oriented code, but they'll be using a lot of libraries where there are classes and objects. So you have to understand how object-oriented programming works internally within Python. What are objects? How does inheritance work? This is very, very important concept. especially if you're using other libraries or even if you're writing any production quality code. Again, this is especially useful if you're also thinking of machine learning engineering roles, where you'll write a lot of production code yourself. Similarly, the math module or the math library is again super duper useful. Lot of simple mathematical operations like log, power, all of that is there. Similarly, you have string, right? Similarly, regular expressions. So for most of these things, it is good to know the internals, right? Again, in the worst case, you should know how to use these. When I say you have to know internals, like for example, imagine if somebody gives you a string, right? And you want to let's say build a function which does some string comparison, right? Let's assume there is a string comparison function which compares two strings, right? Even if this is not available, you should be able to implement it on your own, right? That's what I mean when I say that you have to have an internal understanding of it. But in the worst case, you should at least know how to use this stuff. Again, especially imagine if you come from a non-CS background, you might not know how regular expressions work under the hood, because that is a topic that you typically learn in theory of computation, right? So there is finite state automata or finite state machines that are typically used to recognize regular expressions. And especially if you come from a non-CS background, you might not have studied this topic. So that's okay. So in such a case, especially for topics like regular expressions, even if you don't know how things work under the hood, you should at least know how to use it, especially if you come from a non-CS background. But if you come from a CS background, because you have studied theory of computation and especially finite state machines or finite state automata, you're also expected to know how a regular expression is recognized under the hood. Again, if you want to know most popular string manipulation functions or regular expression related stuff, it's just a cheat sheet away, right? Again, cheat sheets are super useful to help you understand what to prioritize and what not to prioritize. Similarly, let's look at date time functionality, right? Because in machine learning and data science, especially in data science, when you're doing data analysis, you do a lot of date time operations. Time data is there in a lot of data sets. Similarly, you use a lot of OS functionality, right? So either to open a file or to say, hey, what all files are there in a folder, all of these stuff. There is an OS module which is very popular. Having a good understanding of them is super duper helpful. Especially if you come from a CS or IT background, understanding how this OS module works is super helpful. You have to understand the internals of it. Again, if you come from a non-CS background, that's okay. You should at least have a user level understanding of these. Again, date time functionality is very simple. Having a good understanding of what's happening under the hood is fairly straightforward. It's very, very simple. Most operating systems and most libraries use Unix timestamps and things like that. Very simple to understand, nothing very complex or rocket science there. Cool. So similarly, file handling, right? So again, simple file handling. How do you read a file? How do you write to a file? How do you append something to a file? All of the basic file handling stuff in Python itself. Again, if you come from a CS background, it's good to know the internals of how things work. If you come from a non-CS background, at least having a user level understanding. Again, you'll find lots of cheat sheets for this. You could just use it, and that's good enough. And equally importantly, a topic that's often overlooked is multiprocessing and threading in Python. This is very, very helpful, especially, again, understanding how this works. The internals is super duper important. You should be able to write basic multiprocessing and multi-threading code, because in data science and machine learning and AI, oftentimes you will have to use multiple threads and multiple processes to speed up your job, right? This is a very, very often overlooked concept, but it is super duper important. Having a good understanding, again, we suggest our students and learners to have a good internals understanding. Like for example, let me give you a simple example here, right? If you have two matrices A and B, can you multiply these matrices using a multiprocessing code? For this, you have to understand the internals of how multiprocessing works in Python, right? Again, simple stuff like this is super duper useful. Very often points of discussion, especially if you come from a CS background, especially at top product-based companies. Very, very popular question, especially for machine learning engineering type of roles, right? Cool. So these are some of the most important things with core Python. Again, this list is not exhaustive, but these are the most widely used that we use day in and day out as far as data science and machine learning is concerned. Next is R programming. As I was just mentioning a while ago, this has a label G, which means it's good to know, right? If you know this, good. Again, knowing more never hurts, but it's not a must know, right? Again, there are some teams and organizations which use, there is a lot of older code, right? Because earlier, pre-machine learning, there might have been some stats folks who built some models. Especially, I've seen this a lot in banking and financial services, right? So there are some of these industries where statisticians have written lot of earlier code in R programming. And you might have to understand that code and modify that code to your needs. So there are some teams and organizations that use. So when I say it's good to know, not a must know, even if you don't know it, you should have the ability to pick it up. You can just read some, again, if you already know Python programming, all the basic fundamentals, picking up another programming language like R, again, you don't have to be an expert in it. You should just have the basic knowledge to read others' code, modify others' code, probably write short snippets of code. Again, you can pick it up in a week's time if you already know Python. So it's a good to know, not a must know. Cool. So now let's go to some interesting Python libraries. I'll go to each of these libraries and explain to what depth you can learn these. So first is NumPy, right? The most popular library for numerical algorithms and numerical processing. Very, very popular, extensively used. Again, a lot of other libraries actually use NumPy internally, right? You have to understand the internals of how NumPy works. This is super duper useful. Again, if you're not sure, NumPy is a huge library, just use a cheat sheet, right? So for example, in NumPy, there is this data structure called ND array, right? Very, very useful, very, very popular. It's used literally everywhere, right? Lot of, like scikit-learn uses NumPy's ND arrays internally. A lot of other libraries also do. So understand how ND array works, how ND array is stored in the memory, why NumPy is so fast, right? So these are very, very useful stuff. Again, you should understand the internals of NumPy. Cheat sheets can help you at least prioritize what to learn, because it's impossible to learn everything in NumPy. On a daily basis, I keep forgetting some functions in NumPy. I do a Google search or I just use a cheat sheet, right? It's very common, nothing wrong with it, happens to every one of us, but understanding how things work under the hood is very helpful. Similarly, scientific Python, right? Lot of libraries, lot of statistical functions, lot of plotting, lot of simple, like if you want to, let's say, have a curve, let's say you may have a curve and you want to find the area under this curve. Very often used in machine learning. For example, you have area under the curve, area under the ROC curve that we have to do, right? If you want to find what is the area under this curve, we often use scientific Python, right? Again, especially for the most important functions, you have to understand how this is working internally. For example, area under the curve, right? You should, if required, you should be able to implement it on your own without SciPy. Only then you know the internals of SciPy and how it works. Similarly, cheat sheets are super helpful because SciPy is a super large library. Super large. It's impossible for me to keep track of NumPy and SciPy because so large. I Google search very often, just like most of you. And I've seen a lot of data scientists, machine learning folks just Google search or use cheat sheets. Similarly, the other library that most of you may not have heard of is called Number, right? Again, Number is basically, what it does is it uses just-in-time compiling, right? So again, without going too deep into just-in-time compiling, so it does two things. It does just-in-time compiling to take the Python code, especially the NumPy code that you've written, and converts it into machine-level code. It converts into raw machine-level code as and when it needs to do that. That's why it's called just-in-time compiling, so that your code runs much, much faster. And it can optimize based on your CPU architecture, based on your GPU architecture, and it can also do a lot of parallel processing. It can do a lot of parallel processing inherently without you having to worry about it. So you can simply write a NumPy-like code and just use NumPy's ngjet, right? Which is a no Python just-in-time compilation strategy that Number uses internally. And this can help you speed up a lot of NumPy code using multi-threading. Again, NumPy internally uses C++ and C, right, for most of its functionality. But Number can actually use the just-in-time compiling to actually generate machine-level code, which is typically faster, and also parallel code, right? Again, you don't have to be an expert in Number, especially if you don't come from a CS background. You don't understand what is just-in-time compiling. Don't worry about all those details. This is good to know, right? And again, you don't have to know a lot of internals. Just having a high-level intuition of how it works, just reading its official documentation is good enough. Again, the purpose of Number is it can speed up your NumPy code and it can do parallel processing on your NumPy code, That's why it's so, that's why it's sometimes used, not always. And I'm not saying NumPy is the only important library. You can pick any similar library that can speed up and parallelize your NumPy code. Right? Again, NumPy is one of the popular ones, one of the more stable ones. But pick up any such library and you're good. Again, NumPy is not so popular, but it comes very, very handy if you're doing processing on large matrices in NumPy or large tensors in NumPy. Okay, so again, I just covered NumPy here because of NumPy. More importantly, you have to understand Matplotlib. Super duper useful, one of the most fundamental plotting libraries. You have to understand the internals of how it works. For example, imagine you're plotting a histogram. Imagine you're plotting a simple histogram using Matplotlib. You have to understand how this histogram construction is working internally. And again, cheat sheets are super helpful because Matplotlib is also a very large library. Again, once you know Matplotlib, there are other libraries which are good to know. For example, there is Seaborn, which does a lot of statistical plotting that you need. More beautiful plot, but Seaborn itself is built on top of Matplotlib. This is good to know, not a must know. Even if you just know it at a user level good enough, cheat sheets are super helpful here. Similarly, there is another library called Plotly, right? Again, Plotly is super popular because you can use Plotly plots and actually deploy them on the web, right? Again, this is good to know. You have to at least know Matplotlib. Matplotlib is a must know, and you have to understand the internals of it because it's so widely used. Knowing additional libraries is helpful, right? It's good. Plotly is good to know, especially if you want to have your plots on the web, right? There is something called as Dash, which is again built by the same Plotly team. If you want to do, let's say, some web-based data visualizations and interactive data visualizations, right? So it's good to know. All you need to know is at the user level. You don't have to know too much of internals behind it, and simple cheat sheets are super helpful. Similarly, there is the JSON module within Python libraries. This is super useful because you typically see a lot of data that is stored in JSON format. And JSON is what is used extensively by web APIs, right? Imagine if you're productionizing your model, you typically end up using the JSON module. You have to understand what is the JSON data format, the internals of it, and cheat sheets there are tons of cheat sheets to help you get used to JSON itself. Cool. So next thing here is Pandas. Okay. Again, super powerful, especially the Pandas data frame is literally the workhorse of modern data science operations on data in general, right? You have to understand how Pandas works internally. Super duper helpful. Again, you can use cheat sheets because Pandas is a fairly large library. Now, there is this library called Dask. Again, this is a younger library than others. What Dask does is, Dask can parallelize a lot of your data operations, right? It's an up and coming library. Again, this is primarily used if you want to parallelize or if you want to do distributed computing, right? Suppose, imagine Dask is much more of a lightweight option. There is obviously Spark that is more extensively used when you have large amounts of data. But Dask is a much more lightweight option as compared to Spark, especially if you want to do distributed computing on Pandas and NumPy and things like that. Again, you need not be an expert in Dask, but if you know it at a user level good, if you understand how it works at a high level good enough. Again, this is good to know, not a must know, because Spark is much more popular for data science and machine learning applications when the data is large. Dask is, again, in a couple of years, Dask might become more popular than Spark. Who knows, right? So again, simple cheat sheets are super helpful. One other simple note here is, especially if you're interested or if you're coming from a distributed computing background, right? For example, suppose imagine you're a data engineer, right? Who already works on large amounts of data and distributed computing. Having good knowledge of these libraries is an additional bonus, or it's good to know, right? Because these are nothing but distributed computing and parallel processing libraries on top of Pandas and NumPy that you already use in data science. Cool. So next, other tools and technologies which are very, very fundamental. The most important probably will be Git itself, right? Again, a lot of us, we write our code, we commit our code, we commit our models. You have to understand how Git works and how to use it fairly well. Again, I'm saying I by you here because I would actually strongly recommend that you understand how Git works, where is it used, when to use it and when not to use it. Again, there are tons of cheat sheets, very simple toolkit. Again, we have done live sessions in the past about Git. Very simple, very easy to use. Or Again, Git is the most popular version control. Again, if you want to do version control on models or if you want to do version control on code, super duper useful. There are also other version control technologies, some of them used by some companies. You could also, even if you know that, that's okay, but I would still strongly recommend Git over others because Git is almost like the standard right now. This will also help you push your code into GitHub, right? Showcase your code and things like that. Other thing is simple terminal commands, shell commands, right? For example, you have to know what is SSH, right? SSH is useful to remotely log in into some box. How to copy something, SCP, right? Secure remote copy. Similarly, you want to, let's say, print something, cat. You want to list all the files. A bunch of popular shell commands because most often you will work on a Linux-based computer and you will have a terminal or a shell and you typically write these to do basic operations. Suppose you're copying some data from somewhere, right? You want to check whether the data is there. If you want to securely copy from another server, you can just do SCP. If you want to log into a box on the cloud, SSH. Basic commands. Again, you don't have to know the internals of how they work and all that. So if you come from CS background, knowing some of these internals is helpful, but just having user level stuff is good enough. Again, there are tons of cheat sheets that will help you with shell commands. Again, there are some of these other libraries like Beautiful Soup. This is something that we do recommend. Again, this is especially useful because in a lot of real situations, you will scrape data from some web page or some resource like that. So Beautiful Soup, what it helps you is once you scrape a page, let's say you scrape a HTML page, a web page, right? Then it can help you extract various parts of this HTML page. Again, you don't have to be an expert at it. Having a user level understanding is good enough. But again, if you know the internals of how Beautiful Soup works, that's better, obviously great. And there are tons of cheat sheets again. Very useful, especially for web scraping and obtaining data from web pages. Again, I'll take your questions at the end of this session. So please feel free to share your questions in the chat window. I'll answer all of them. I just wanted to cover all of these so that we don't miss anything. Similarly, this is probably, I'll put a triple star here. You have to know SQL. You have to know internals of how SQL works. There are tons of cheat sheets, but SQL for relational databases is super duper useful. Of course, you have to know the basics of relational databases and what are tables, what are joins and all that, but you have to be pretty good at SQL for most data science roles. When I say pretty good at SQL, of course, you have to know nested joins and nested operations, right? So you have to be really good at SQL. This is probably one of the most important tools or technologies that every data scientist uses on daily basis. Cool. Then let's go into classical machine learning libraries, right? Of course, the most popular library is scikit-learn. Again, while this is phenomenal for learning machine learning libraries and using it, it's also used extensively in a lot of production environments. So you have to understand scikit-learn internals. This is important. So please don't use, I've seen a lot of people who use scikit-learn functionality as a black box. Suppose they use the k-means, right? They use k-means for clustering in scikit-learn. But the moment I ask, okay, how does this work? How does this imagine if you were to implement this from scratch yourself. A lot of people don't know. So please don't use scikit-learn as a black box. So not as a black box. Try to understand as much as possible on how things work internally. I would actually go on and recommend that if possible, because scikit-learn is open source. I've done this multiple times and it has been super helpful for me. I sometimes go and read the source code of some of the implementations because that has helped me learn much more on how some of the best engineers have implemented the internal functionality of scikit-learn. So you have to know scikit-learn inside out. Of course, there are cheat sheets that will help you prioritize on what functionality you should know more than others. Similarly, very, very popular models in classical machine learning are gradient boosted decision trees. Right? These are literally the workhorse. Again, if you go to any Kaggle competition on tabular data, GBDTs are super good. And for GBDTs, again, scikit-learn also has an implementation for gradient boosted decision trees, but it's not very good. So the best libraries are XGBoost. Again, it's a research work from University of Washington. LightGBM from Microsoft, CatBoost from Yandex in Russia. Learn these libraries. These are not very large libraries. Very simple, very easy to learn, but understand the internals. You should understand, hey, how is LightGBM different from XGBoost? Why is LightGBM lighter and why is it faster? Why is CatGBM performing better when you have a lot of categorical data than XGBoost. What's happening under the hood, right? So again, these libraries are some of the most widely used libraries in the industry. I've seen a lot of people who, when they have some problem, they actually use these libraries, very often even just light GBM, because in most situations this tends to be faster and slightly better than XGBoost in most situations, not all situations, but in most situations. So some people just use XGBoost or CatBoost, doesn't matter. Understand the internals of it. I've seen a lot of people use these as baseline models. Simply, if you have some tabular data, just use these as baseline models. So these, you have to understand the internals of these, especially for machine learning and hardcore data science roles. You have to know these things inside out. Cool. Next comes, of course, your deep learning, which is equally important. So with deep learning, I would say learn at least one of these, more the merrier. Preferably learn TensorFlow 2, 2.0 or whatever version it is right now, right? I think it's 2 point something now. I forgot what version it is, but at least TensorFlow 2, which is the more recent versions of TensorFlow. Keras, very, very good. Again, TensorFlow 2 and Keras are much more tightly integrated now. Or PyTorch. And whatever library you're picking, understand how it works internally. For example, if you're using TensorFlow, right, understand how automatic differentiation is happening internally, right? Understand how an actual model works internally, right? So this is super duper important. Understand the internals. There are tons of cheat sheets. My suggestion is at least know one of these libraries, if not all of them, and more the merrier. For example, in our course videos and live sessions, we cover TensorFlow and Keras. Again, just to give you that context, Keras is very, very popular on Kaggle competitions. And why is it so popular? Primarily because Keras is much easier to write the code in. You have to write much smaller amounts of code to get the same work done as compared to TensorFlow or PyTorch. PyTorch is again very popular with companies like Facebook AI Research Labs and some of these labs, right? I think Tesla also uses PyTorch much more extensively. Google uses TensorFlow much more. Again, there are advantages, trade-offs with everything. None of them is perfect, but at least know one of them, more the merrier. If you have to pick one, I would strongly recommend Keras because it's easier to pick up. That's all, right? But the more the merrier, as always. Similarly, especially if you are developing for IoT applications or mobile applications, learn this library or a component of TensorFlow called as TensorFlow Lite. Again, this is good to know, not a must know, right? But if you are developing applications for Android phones or iPhones or tablets or Raspberry Pi or IoT devices, this is a must know. This is super duper helpful to take complex deep learning models and deploy it on IoT devices. And even here, even if you know it at a user level, that's okay. But if you already know how TensorFlow works, and if you're planning to deploy your solutions on IoT, mobile, again, by the way, also on web pages, that's another thing that I forgot to mention here. So imagine if you want to have a browser-based deep learning application, right? TensorFlow Lite is the way to go. Then it's better to understand the internals of TensorFlow Lite, what it does, like quantization and concepts like that. Not very complex, very simple concepts, very easy to pick up. But having a knowledge of libraries, especially like TensorFlow Lite, will help you deploy for IoT, mobile, and web. And I see a lot more companies and organizations building deep learning applications on mobile and web. There are some in IoT also, but a lot on mobile and web. So that's a good to know library. Next is hyperparameter tuning. Sometimes some people also call this as AutoML. What most modern AutoML does is it's doing hyperparameter tuning, or it's doing some tuning of features, or it's modifying features, or is refeaturizing them, or rescaling these features, or doing some neural architecture search and things like that, right? So there are a bunch of libraries here. Again, pick any one of them. HyperOpt is one. There is another called OpTuner. Keras itself internally has something called as Keras Tuner, right? Pick any one of these. That's okay, right? I mean, no preference. Again, whatever you pick, right? For example, if you pick HyperOpt, right? Whatever optimization it's doing, it's better to have minimal user level understanding. If you have a deep understanding of what's happening under the hood, that's better. No doubt about it, but sometimes this could be slightly complex because this uses Bayesian optimization and more advanced concepts that everybody may not be knowing. That's okay. At least know it at a user level. That's the basics that you should know, and cheat sheets are always available. Pick any one of them, that's okay. And I see every company having their own preference, or different companies building different solutions themselves, especially large FANG-like companies. Now comes computer vision and NLP. Again, lot of modern computer vision and NLP. Oh, sorry, I forgot one more library. Okay, I mistakenly forgot. I'll write that. Okay, so let me write it here anyway. So I forgot Hugging Face. Completely missed. Okay. Okay, so I'll write it and explain this. Okay, so if you're building something around computer vision or NLP, very often you will build a deep learning based solution. You will be building a deep learning based solution, and when you're building a deep learning based solution, you will either use TensorFlow 2 or Keras or PyTorch. Very often. But there will be a lot of instances where you might have to do some low level computer vision. For example, you have a video, right? And you want to extract each of these frames as images. And the best way to do it is using OpenCV, right? Or if you want to do some low level image processing operations, the best way to do is to use OpenCV, one of the most popular libraries for computer vision. Again, you can actually take deep learning models and integrate them into OpenCV. We have done some live sessions on that, right? So you can take a deep learning model, put it into OpenCV and make it execute on some images or video or things like that, right? So for OpenCV, at least have a user level understanding. But if you know more, if you know the internals, especially if you have studied image processing, if you come from, let's say, electronics and communications background, right? You might have studied some signal processing or digital signal processing. Then understanding some of the internals of image processing operations is helpful. Again, OpenCV is a phenomenally large toolbox, very, very large. So cheat sheets are the way to go here. Next, for NLP, right? Again, for NLP also, very often we use deep learning based solutions, very, very often. But there are some of these libraries like NLTK, very old, very popular library, and more recent libraries like Spacey, which can help you do some simple operations. For example, you want to remove stop words. You can do it very easily using NLTK and Spacey, right? Again, for some of these libraries, some of the most common operations in NLP, you should know the internals of it. And of course, as far as these libraries are concerned, they're fairly simple, right? Again, there are tons of cheat sheets to use. It's all about knowing a bunch of classes and functions. But knowing the internals is helpful, at least know how to use it. That's the minimum. Then, as I was mentioning a while ago, there is this very popular library called Hugging Face, right? We have done tons of live sessions on this also. We've used it. So this is primarily for transformer-based models. These are literally the cutting-edge deep learning models. So the whole Hugging Face library is designed to help people build multiple transformer models or use transformer models, especially for NLP applications. So very, very popular, very fast growing library. Must know, almost like I would say, know the internals of it and Of course, there are some cheat sheets, but know the internals of it, because if you already know deep learning, if you know how a transformer works or how BERT models work or how GPT models work, having a good understanding of Hugging Face is a must, including its internals. That's something that I forgot to mention when I was making these notes. Similarly, very often as a data scientist or a machine learning engineer, you will deploy your models using simple web APIs, right? Suppose if you're using a third-party API, we typically use this requests library, right? Which will help you request something from a web page or from a web API, and you get the data in JSON format and things like that, right? So requests library is very popular, very simple. And having a decent understanding of how the request library works internally, how web APIs work internally, at least at a user level is a must, right? Similarly, if you want to build an API of your own, this is what a lot of data scientists end up doing. Especially machine learning engineers, for sure, they end up building a lot of web APIs so that they can integrate their solution with other teams in their organization. So learn about Flask API or Fast API, any one of them, and then learn about a simple Gunicon type of setup so that you can deploy your Flask API or Fast API into a website like structure, into a web server based structure. Again, this is one option, or anything similar is okay. At the end of the day, do you know some technology or some toolkit which will help you build an API of your own, right? Flask APIs or Fast APIs with Gunicon are surely widely used. Again, if you don't know the internals of API, that's okay, right? At least know it at a user level, have a good high level understanding of what's happening under the hood so that you can debug them when things go wrong. Again, you don't have to have the same level of in-depth understanding of APIs like a web developer might have or a hardcore software engineer might have. That's okay. But you should at least have a user level understanding of it. Similarly, if you want model interpretability, this is becoming more and more important. Of course, there are simpler models like logistic regression where we can just use the weights to get model interpretability. But there are two very important libraries called LIME and SHAP. Again, these are the names of the techniques also, right? These are also libraries. Again, we have done some live sessions on these topics in the past. These are very, very important to learn. Knowing the internals of these techniques, knowing how these libraries work is super important, because especially if you have deep learning techniques, if you're deploying a deep learning model and you want to say why this model gave this output, most likely you'll get good enough interpretability of the models through LIME and SHAP. Of course, there are other techniques, but these are some of the most popular ones that we believe are widely and extensively used. Cool. Then comes productionization and ML Ops, right? Especially if you're an ML Ops engineer or if you're a machine learning engineer, these are super duper important. For example, you have to understand the basics of Docker and Kubernetes. You don't have to, as I was telling you, you don't have to be an expert. You may not be a DevOps guy or you may not be a software development engineer. You don't require that level of understanding, but you need at least a user level understanding. And especially if you're thinking of machine learning engineering roles, understanding these is super duper helpful. Again, we've used these technologies in some of our case studies where we give you a high level intuition of what they are, how they work internally with some code snippets and actual deployments on a simple on a Docker container. Similarly, especially for productionization and ML Ops, pick any one of these, right? You should know, like for example, SageMaker is an AWS based ML Ops platform. Kubeflow is an open source platform from Google which works on Kubernetes. There are also other technologies for ML Ops like MLflow, there is Azure ML, pick any one of these. Again, for all of these technologies, you might not be an expert in ML Ops or you might not be a DevOps guy or a software development engineer. So at least understand them at a user level. Again, these are super duper useful again if you're looking for machine learning engineering roles. At least one of them, if not all. Pick any one of them and that's good enough. Again, we have tried to cover some of these. We have covered SageMaker, we have covered Kubeflow in our course live sessions. We have not covered all of them, obviously. Cool. So then coming to big data, what should we know? What tools and technologies we should know in big data? I would recommend Spark very, very actively. Again, Spark, you should at least know it at a user level, at an intuition level. Especially if you come from, let's say, if you come from CS background, right? Or if you come from, let's say, data engineering background, then knowing some of the internals is always helpful, right? Again, we've tried to cover some of the internals also in our course videos and live sessions earlier, but not too deep like a standard undergraduate CS course in, let's say, distributed computing or a graduate level course in distributed computing, right? Again, there are lots of cheat sheets. The most important stuff in Spark that you should know is obviously PySpark, because most likely you'll not write code in Scala or Java, most likely you'll write it in Python. MLlib, which will help you train machine learning models if you have large amounts of data. And Spark SQL, which can help you actually write SQL-like queries if you're operating in like hundreds of terabytes of data. So Spark is very, very mature, very, very widely used. I was also talking to you about Dask earlier, right? Dask is a much more recent library, a recent tool as compared to Spark. It's much more lightweight, but Spark is much more widespread in the industry now. So similarly, in terms of NoSQL databases, again, you don't have to be experts in it. Because you're not a software developer or you're not a back-end developer, right? So at least you should have a user level understanding. These are good to know, not a must know. These are good to know, especially if you if you want to go into a machine learning engineering role, learning some of these is helpful. We have tried to cover some of these, not all of these in our course live sessions and things like that. We have certainly given intuition of almost all of these. And again, there are tons of cheat sheets. For example, MongoDB. Especially if you have document stores, right? If you want to store a lot of text related data and document related data and things like that, MongoDB is super powerful. Similarly, if you want to build a search engine, Elasticsearch is a very popular choice. Similarly, if you want to store large amounts of data in a distributed cache, Redis or Memcache. Again, I'm not saying these are the only tools that you should know, but these are the three most popular tools used in data science and machine learning workflows. Again, knowing something similar is also okay. Somebody might say, hey, I know Cassandra. That's okay. Knowing some of these will give you a sense of, okay, in case you're in a situation where you have to work with the software engineering team and you have to recommend what might work well in your situation. So for example, I learned many of these technologies when I was working on actual projects by discussing with my software engineers, my software development engineers on what might work better for machine learning needs and what might not work well, right? So at least a user level, high level understanding, these are good to know, not must know, but knowing them never hurts, at least at a high level. Cool. Next comes dashboarding and UI, right? Again, if you know Tableau or Power BI, that's good to know. Like for example, we have done some live sessions on Tableau, not on Power BI yet, right? If you know it, good, because you can do simple dashboarding very quickly. And you don't have to know a lot of internals, even at a high level, at a user level, if you know, that's good. Similarly, if you already know Plotly, Plotly has built a tool called Dash. It's basically a library through which you can actually build web-based interactive UI, just like Tableau or Power BI, but with complete control. Right? This is like you can write Python code or JavaScript code and you can build a visualization, an interactive visualization as powerful as Tableau or Power BI using Dash. This is again an up and coming library or tool, which is especially popular amongst data scientists and machine learning engineers who already know how to program, right? Because this gives them a lot more flexibility on what they should do. Similarly, especially on the UI front, if you're building some demo and you want to showcase it to other members of your team, those are typically called as data apps. And if you want to, suppose you don't know web development, right? Most data scientists may not know web development, but you have a simple app. Let's say you've built some, there are images, and in that image you want to detect what all objects are there. And you want to show this demo to other members of your team. For this, you want to deploy it on a small web server so that your team across the world can see it and give feedback to you. You're building a simple UI or you're building a simple data app. For that, there is a very popular library called Streamlit. Again, we have covered some examples with this. Streamlit or anything similar is okay. Again, this is not a must know, this is good to know. And you don't have to know about how it works internally, all the technologies of web development. But even if you know it at a user level, that's good enough. If you can use it, again, this will help you showcase your work both to recruiters and other members of your team. Similarly, now comes the big behemoth, which is cloud computing. How much of cloud computing should we know? Again, cloud computing, whether you're using AWS, which is Amazon's web services, Azure or Google Compute Platform, most of these are good to know. If you know them, that's good, right? And all you need to know is at a high level, user level is good enough, and there will be tons of cheat sheets. Again, this is not an exhaustive list, but these are some of the technologies in the cloud that are often used in data science and machine learning. For example, often we store our data. Large amounts of hundreds of terabytes of data, we might store it on the cloud. So Amazon has something called as, or AWS has something called as Simple Storage Service or S3. Right? I'm sure Azure has something similar, GCP has something similar, right? Again, I'm talking about AWS because I have used it extensively over more than a decade now, right? So I've used it more extensively. While I know some of Azure and GCP, I'm no expert in these as compared to my knowledge of AWS. That's why I'm giving you AWS examples. Similarly, if you want to compute, how do you get cloud compute, right? You have EC2 instances, or you can use serverless compute like Lambda. Again, these are all good to know. Please understand that these are good to know, not must know. If you know them, it will help you become a good data scientist or a machine learning engineer. And most of these are good, especially if you're looking for machine learning engineering roles, where you work with teams that already are on cloud and things like that. Again, just user level is good enough. You don't have to be an expert at any of these. Similarly, if you want to use a platform as a service like setup, like for example, Heroku, right, or Amazon AWS Beanstalk, this will help you deploy your apps much more quickly, much more faster than like a full-fledged EC2 or a SageMaker type of stuff. Or any machine learning platform like SageMaker in AWS, Azure ML and things like that. Similarly, Spark and Hadoop, again, Spark being the more higher priority than Hadoop. So if you want to have Spark on cloud, especially on AWS, there is something called as Elastic MapReduce, through which you can launch a Spark cluster. Again, please understand that knowledge of some of these cloud technologies is good to know. Many of these things we have covered in our course videos or live sessions or optional videos, just so that students can pick them up as and when they feel the need or for their current background or role, it is important. So the most important skills, again, let me reiterate this. The most important skills as far as these libraries, tools and technologies is strong foundations. You have to have strong mathematical foundations and strong programming foundations. Once you have this, you can pick everything else if you have the right mindset. Your mindset should be all about flexibility. Don't fix on one library because your team or your org might have different priorities because of historical reasons. So have the flexibility to pick up whatever tool is needed to get the task done. Again, it's all about reading references or documentation, right? Again, you don't have to be an expert in every library that you pick up and use. All you need is basic user level understanding, basic high level understanding of the details. And documentation typically gives you that without having to worry too much about the internals. And the equally important thing is the ability to learn new concepts and adapt as and when required. Again, the ability to adapt and flexibility are related. But again, these technologies will change. 2 years down the line, these technologies will 99% change. We don't know what will be the new hot thing. And of course, at the end of the day, all these tools, their job is to simplify the life, is to simplify. Again, machine learning requires significantly more simplification in terms of tooling, right? And thankfully, things like Kubeflow, SageMaker, they're in the right direction because they help data scientists, machine learning engineers focus on the actual data science work and not on the miscellaneous tasks. So please have an open mind, build that ability to learn and pick up new libraries as and when they're needed, build the ability to read the official documentation and references or tutorials, right? Very often for most good libraries, you have great tutorials. You should build that ability. And this ability comes from strong foundations in programming, right? Have the flexibility, be respectful to your team members, to your organization, because they have historical reasons on why they picked one technology or tool over others. Cool. So these are some of the most important tools and libraries that we felt that we have seen people use extensively. Again, this is by no means an exhaustive list. So let's move on to Q&A now, and I'll just change to Q&A. Cool. So feel free to post your questions in the live chat, and I will answer these happily. Cool. Just a second. Cool. So, okay, so one interesting question here. What about PyCaret? Again, PyCaret is used, but again, it does sort of like some AutoML work, but again, AutoML is still in its infancy. I can put PyCaret very similar to some hyper-optimization based tools or some tools which does feature transformations, try multiple feature transformations, etc. So you can put PyCaret in that same bucket. Again, I've not seen it used as extensively. Again, I've seen a lot of tutorials of it on the web, but in the actual industry, actual data scientists, I've not seen them talk too much about it or use it as extensively as other libraries. Cool. Feel free to ask me questions. I'll happily answer. How do we remember so much programming, AI, LLD, HLD? Vasu, that's a nice question you asked. It's not about remembering. Like if you ask me, I'm really, really bad at remembering things. I have been in terrible situations where I forget the name of one of my friends or colleagues in a meeting and I say, hey you, I'm so bad at remembering things. I mean, I am probably one of the worst people in terms of remembering things. So in terms of remembering things, try to think of this more as, can you arrive at it from first principles? So suppose if you ask me, right? If you ask me about support vector machines today, I probably don't remember at the top of my mind. But if you give me 5 minutes, right, I can derive it from first principles because I know what's happening under the hood, right? Similarly for libraries, for example, if I don't write, let's say Python code for 1 year, let's just assume hypothetically, I will become very, very slow at it. I will even forget basic syntax of writing, of manipulating a simple NumPy ND array because I've not been practicing. Practice is the key. If you're not coding on a regular basis, you will forget, just like any of us. Like for example, I have not written, let's say Java code for many, many years now, and I've forgotten the basic syntax also. So if I have to pick it up again, I will take a cheat sheet, I'll take a simple tutorial, quickly read it and start practicing. So there is no escaping that fact of practicing, but while practicing, we often, especially if you pick up a new library, we all forget. Like I forget left and right. For example, I have cheat sheets for simple things like pandas and matplotlib because I forget what is that parameter supposed to be. I don't remember it at the top of my mind. I either go to the official reference and read up the documentation very often. You might have seen this in a lot of my videos also. I forget what that parameter is. I go to the official reference and read it. That's perfectly okay. Or I have a cheat sheet where I refer to it and say, hey, this is how it should be done. So as long as you have the ability to strong foundations in programming and math, and as long as you can figure these things by either reading the official reference or by working out the stuff from first principles, you're good. Don't worry about it. So what is the percentage role of feature engineering and feature selection? Very nice question from Asgar. So very nice question. The reason being, again, it depends on where is your project. If your project is at a mature stage where you already have version 1 of your system, you already deployed it, it's already in production, right? If you're at that point and you want to improve the models now, you want to improve it, you want to try new things, then feature engineering is what you do. Of course, feature engineering not just necessarily mean that you will only do some feature transformations and stuff like that. You can do complex feature engineering tasks, like you can use matrix factorization for arriving at new latent variables or latent representations. You can use autoencoders or some deep learning technologies like autoencoders to get a vector representation of things, right? So feature engineering need not be just simple feature transformations. It could be about getting interesting feature representations or dense feature representations using deep learning or matrix factorization like techniques. That's one direction. Second direction is very often you try to get new sources of data so that you can come up with better features. So once you're at a stage where your system is already productionized, it's already live, you spend easily about 70-80% of your time on improving the system through feature engineering, trying out newer models, and trying out new sources of data. You can spend 50 to 70% of your time just on feature engineering. Again, feature engineering doesn't just mean feature transformations. It could also mean that you're trying out newer models to come up with better featureizations, which you will encode and put it in your original model itself. So feature engineering can involve a lot of modeling also implicitly. So this is Prathveen. So he says, explain the role of ML in cyber security. Very nice question. So I'll go a little tangential here as the question is interesting. So in cyber security, what do you have to do? There is a regular, so look at any cyber security system, right? There is a regular behavior. For example, I log into a computer, I access the data, I run some SQL queries, I obtain some data, I build some models. This is the regular behavior. And there could be anomalous behavior, right? Somebody, right, trying to suddenly come onto your servers and let's say pull or access some folders which they've never accessed in the past, right? For whatever reason, right? Or they're trying to dump large amounts of data or run very bulky SQL commands on your databases. So this is anomalous behavior. You can detect anomalous behavior using a spectrum of techniques in machine learning called anomaly detection or outlier detection techniques. They're extensively used in cybersecurity, but it requires a lot of deep domain expertise. So for cybersecurity, anomaly detection techniques are widely used, but the feature engineering, to do the optimal and ideal feature engineering, you have to understand the business context and what sorts of behaviors are suspicious or anomalous. So it is used. I have seen a lot of startups, especially out of Israel, who are building really advanced machine learning technologies to detect cybersecurity attacks. Very nice. So Shubham has this question. Any good library or tool for feature stores? Very nice. So depends on where you are building it, right? Let's take about feature store. Again, we have done some video on feature store, how it works internally or on our YouTube channel. You can check it out if you don't know what is a feature store. So in short, feature store is basically a repository where all the features are stored. In nutshell, that's what it is. Again, if you are building your solution on SageMaker or any cloud-based like Azure ML, they give you a feature store. They already give you that, right? And it's typically implemented using a distributed key value or a hash table. If you have to implement it yourself, if the feature store is small, you can just store it in a hash table. Very simple. But if it is large, you can use a distributed hash table, which is Redis or Memcache. Again, the reason I'm suggesting this is you can very easily query the feature store, right? So you can implement your own feature store using simple hash tables if it's a single box implementation. If it's a multi-user large-scale implementation, use Redis or Memcache. Or there are obviously other NoSQL databases which can also do it. You can even use simple relational database, right? You can simply say, hey, I will index by the feature name and I'll get all the feature representations. So feature name will become the index, so I can get this data very, very quickly. So it's all about the data store choice. What operations do you want to perform on the feature store? What database, whether it's relational or NoSQL, serves that purpose? Redis, Memcache are very good choices there. Cool. So please share your experiences in market mix modeling. Venkatesh, so I think we've done some sessions on market mix modeling earlier. So please check out those videos. I don't recall whether they were public live sessions or for course enrolled students. I don't recall that, but we have done those sessions in the past where we've gone into the details of how classical market mix modeling works, how you can use state-of-the-art techniques for market mix modeling and things like that. So Yash says, what drives you into teaching? Why didn't you continue in development? So Yash, so at Applied Roots and Applied AI course, as much of teaching as I do, I'm also involved in a lot of development work. So to be frank there, I think because it's a startup that we bootstrapped and built with all of my co-founders and engineering team, I end up doing equally good amount of high-level design, system design, doing the whole design aspect of, maybe not low-level coding per se, but certainly a lot of development, evaluating code or doing code reviews and stuff like that. I do more of it at Applied Roots and Applied AI course than I did at Amazon. Because at Amazon, we had a dedicated software engineering team and they were doing a lot of that work. Only a small component of it was coming to me, right? At Applied AI course, I spend regularly good amount of time on high-level design discussions, system design, code reviews and all of it. So I end up doing a lot of actual both software development, web development, both front end, back end, also a lot of development on the cloud, and of course machine learning stuff. Cool. Okay, this is a very often asked question, so I'll take it. So software engineer versus machine learning engineer as a long-term career path. At the end of the day, there is no one right or wrong path. Whatever you choose, most importantly, become an expert at it. Because once you, in the first 2-3 years, it doesn't matter as much. But whatever path you pick, try and become really, really good at it. Try to be in the top 1% of software engineers if you choose software engineering path, or try to be in the top 1-2% of machine learning folk if you're in that. Because in the long run, what matters is within that role, are you in the, because that's what will define whether you will become, let's say, a vice president of engineering at a FANG-like company, if 15 years or 20 years into your career, right? So the depth of knowledge and the breadth of knowledge and the actual experience of building things, that's what matters. You could be a phenomenally good software engineer, or you could be a phenomenally good machine learning engineer. Equally, you could be an average software engineer or an average machine learning engineer. There it doesn't matter. What is important is to strive for that deep expertise, building things, deploying things, and gaining that breadth and depth of knowledge. Then there is no wrong path. I've seen phenomenally good software engineers, like superb software engineers who know nothing about machine learning, and vice versa. I've rarely seen people who are brilliant at both software engineering and machine learning. That's very rare, very, very rare. But there is no wrong choice there. In the long term, whatever you pick, whether it is as simple as, let's say, mobile development, become a super duper expert at it. Can you become applied scientist without masters? Yes, Karthik. So at the end of the day, companies, whether they're small, startups, product-based companies, in the long run, your degree only will get you very little value in the long run. See, straight out of your degree, you will have value for the degree. Surely, no doubt about it, because the degree shows that, yes, this guy has the ability to do coursework for 2 years and gain that ability. That's great. But in the long run, your skills are what matters. So I have seen only bachelor's degree students, no master's degree, 4-year bachelor's degree people who have gone on to become applied scientists and excelled at their work. Again, the same applied scientists could also be PhDs. At the end of the day, once they get into that role, what matters is the work they deliver. Like for example, I've had a lot of PhDs working in my team, and I don't have a PhD. But at the end of the day, my manager would evaluate me not whether I have a PhD or not, what matters is who is getting the work done. who is making the progress, who is doing the hard type of work, the most challenging work, who is delivering results. That's what matters in the long run. In the short run, having a master's degree is helpful, no doubt about it, especially if it's from a good university with great curriculum. That's what is super important. Yes, this live session will be available on YouTube itself. Right after this, it will be available. I'll also, the notes that I have written, I'll post it in the description box and in the comment section so that you can check it out. And we'll also add it as an optional video in our course videos. Oh, very nice. So Nayana says that, okay, I think, okay, Nayana says, I don't know whether Nayana is a female name. Yeah. So she says that, that she has 10 years of expertise in business intelligence and data warehousing. And data science is such a natural path forward for you, right? Because you've already done business intelligence. Business intelligence is mostly basic statistics, basic data analysis. Once you go a little above and do predictive analytics and machine learning and deep learning, that's what most modern data science is, right? So it's a very natural transition. I've seen a lot of people from similar backgrounds like data engineering, data warehousing, business intelligence, databases, comfortably move into data science even after 10-15 years of work experience. Cool. Any other questions about this specific live session? I see a lot of general questions because students or learners are here for this specific topics. I would like to see more questions on this specific topic than general topics because that might be helpful for everyone. And we can certainly conduct a general live session in the future for all sorts of questions. We'll be happy to take those. Very nice question. This is from Uttej. Uttej says, there is a lot of stuff to learn. How much time does it take for an average learner to master and learn the required skills? Very nice question. So from our own data of students, right, we typically see this. For an average student, we are not looking at like people who already know data science, right? People who are already phenomenal software engineers, or we are not looking at that. For an average person in our course, if they're spending 12 to 15 hours a week, approximately 2 hours a day, maybe a little more in the weekend for revision and things like that, right? They typically spend 6 to 9 months. Of course, different people get stuck at different points. So we have some people who get stuck in coding, we have some people who get stuck with the math, but irrespective of that, typically we see people like somebody who is really diligent can finish everything in 6 months because we have covered most of these things, if not all of these things in our course videos and in live sessions. Typically 6 to 9 months is a good valid period, maximum 12 months. As long as, again, here the most important thing here is, are you willing to put in dedicated 2 hours of time on regular basis? If you do that, I think in 365 days, there is nothing that is stopping you from learning these technologies and having a successful career transition. But remember, you may not become an expert right away. Let's not fool ourselves that you'll become an expert. You will learn all the basics and you'll have the basic know-how, if not full in-depth of every topic. But certainly you'll have strong foundations in mathematics and programming that you can transition. On your job, you will learn a lot. That's what happens to a lot of our students. Okay, so Rajesh is saying, what about 3D deep learning libraries? Nice question. So we are already planning these live sessions on geometric deep learning, which is a very nice evolving field right now, wherein, so typically deep learning is used on images, text, time series and things like that, typically, or simple tabular data. But imagine if I have a point cloud, right? In computer graphics, it's very useful. Or imagine if I have some protein structure, which is like a graph, or if I have a social graph. So imagine if I have some of these data sets, there is a whole area that is very fast evolving in the last year to two called geometric deep learning. So we will be doing we'll be doing a series of live sessions explaining geometric deep learning, and you can build a lot of geometric deep learning based stuff using TensorFlow, Keras or PyTorch. You don't require another library, right? Simple, these libraries are sufficient. There are some instances where you might have to use, especially for 3D point clouds, you might have to use OpenCV, but otherwise it's fairly simple and straightforward. Okay, so for Vikas, Vikas is saying, what is the sequence of topics to learn for a non-CS guy? I would recommend the same sequence that we described right now, right? So start with basic Python first, simple shell scripting, SQL. The same sequence that we explained right now is, I think, a good sequence to learn of tools and technologies for a non-CS guy. For a non-CS guy, you might have to spend a little more time on Python, basic programming, or basic SQL, because you don't know it. You have to first get slightly comfortable. So for non-CS folks, you might end up spending 2 to 3 months getting the hang of programming, getting the hang of SQL. But then once you get the basic hang of things, things will move very fast. Even for non-CS people, we typically see them, as long as they're diligent and disciplined to put in those they typically tend to put in closer to 15 hours a week and not so much 12 hours. They typically put in those 15 hours because they have to learn a lot of programming and practice. They typically take about 10 to 11 months, typically, because they need little additional time to get comfortable with programming or to doing coding assignments and things like that. So this is Yoginder. Again, it's a tangential question, but I'll still take it. I'm a BCom major and I want to learn data science. What should I progress? Yoginder, my suggestion for you is, because you have a commerce background, I would strongly recommend that you do a master's degree like an MCA or an MSc computer science, so that you learn some of the basics there, right? Because I'm assuming, because you come from a commerce background, I'm assuming, I could be wrong here, that you have not studied so much mathematics at 11th and 12th class, and that could be hindering, because there is a lot of calculus and linear algebra that we will use in machine learning, right? So doing an MSc computer science or an MCA, you will learn some additional mathematics as part of the coursework. You'll also get slightly comfortable in coding. So we would strongly recommend you to go to that path where you're doing a 2 years master's degree, like a MS computer science or MS mathematics or MCA, better still, right? So that your transition to data science careers is much more smoother, and you have a computer science degree. Again, as I was just telling you earlier, degrees are certainly useful to get your foot in the door, to prove. What degrees prove is this, that you have spent considerable amount of time learning the basic foundations. The better the university, the better is the value of it, obviously, and you have the right skills. So they'll surely help you right out of the gate. In the long run, it may not matter as much, but to get into your first job or your second job, degrees do help. That's the reality of it. So, okay, Venkateshan has a nice question, which is any guidance for current data scientists? So, my suggestion that I've always told people that I've mentored, I've also been told this from some of my managers and mentors who have been phenomenal in my life. Like I've been extremely fortunate to have had very wise people mentor me. Like my last manager at Amazon was closer to my dad's age. He has seen the ups and downs of Silicon Valley. He has been at a lot of startups. Phenomenal guy, life's lessons literally in my one-on-one meetings with him. So one of the things that I learned from all these people, both from my mentors and from mentees, is if you want to excel as a data scientist, or for that matter anything, even to excel as a software engineer, spend at least 5 hours a week on learning new things. It could be reading research papers. Like I think Venkateshan, you were talking about this fact that I believe you were an AI student earlier and then you transitioned into data science careers. I think you mentioned this a while ago, and you're working on market mix modeling. So my suggestion is this: read all the cutting edge research papers, blogs, everything about market mix modeling, the cutting edge stuff. At the same time, maybe you want to spend a couple of hours on that. Parallelly, learn for a few hours every week completely new concepts. For example, in market mix modeling, now can we use state-of-the-art interpretability models like LIME and SHAP? Yes, you can, because SHAP comes from strong computational economics or economic mathematics, right? So the idea here is spend 5 hours every week, either reading research papers, technical blogs from various companies, or learning new libraries, right? So imagine, like for example, Dask is there. You could spend like a couple of hours a weekend reading and understanding what is Dask, why is it different from all other libraries, how does it work internally. 2 hours. If you do this for 2-3 weeks, you understand the internals of how Dask works. You can do simple experiments yourself to see why Dask is slightly better than Python or Python Pandas, and why is it still not there with respect to Spark and other things. right? So spend those 5 hours on learning continuously. If you don't do that, especially in a fast evolving field like data science, you will become a dinosaur in 5 years. I've always joked with my mentees and said, guys, if we don't spend 5 hours a week learning, we'll become dinosaurs in 5 years. So that's my recommendation, Venkateshan, for somebody like you. Read technical blogs of large companies who have already built it and done it, right? Similarly, read research papers, code libraries, and things like that. Very nice question from Indranil. Okay, what is meant by internals? Very nice. For example, to know the internals of a list, do we know how lists are constructed via structure in Python, or to implement any function like reverse? Very nice. I really like this question, Indranil. I'm happy you asked it. So there are two parts to that. First is, so in internals, there is a simpler thing, which is what you said, like given a list, can I implement the reversing a list, right? Or taking a subset of elements from a list. Can I implement it on my own without using the inbuilt functions? That's one level of understanding. The second layer of understanding is, how is list implemented in Python? It's implemented using something called as dynamic arrays. Again, if you especially come from a CS background, right? Wherein, because you already know how memory is organized, how paging is done, right? How memory reallocation is done, because you learned it in your C programming. I'm sure you learned it in computer organization and operating systems, right? So having the deeper understanding, for example, how is a list organized internally? List is basically a dynamic array at the end of the day, right? So why are operations on list order of 1? Some operations, and some operations order of n, right? So there are two levels of understanding. The minimum that you should understand is to be able to implement things like reverse. That's the minimum. But if you come from a CS background, go one level below. And there are very nice blogs which explain this. It's just a Google search away, right? On how a list is implemented internally using a C structure or a C++ object. I think it's a C structure if I'm not wrong. Yeah, I think it's implemented using a C structure. Look at what are each of the parts of the C structure. Look at how memory is being allocated and reallocated, right? That's better. The deeper the knowledge, the better. But of course, most people don't expect non-CS folks to know it, because the non-CS folks may not know how computer organization works, how memory management works, how operating systems do paging. They may not know it, and that's okay. The minimum is the reverse function or the equivalent functions. The deeper, the better, obviously. Very nice question. I'm happy you asked it. So Ram Sai has a nice question. How in-depth should we know data structures and algorithms for machine learning roles? Again, it depends a lot on the role in the company. So we have a dedicated video on various roles at various companies and what to learn. So to put it succinctly, right, for data scientist roles, you don't have to know the same level of CS data structures, algorithms like competitive programming level. You don't require to know. For data scientists, even at FANG companies, because we have some of our students who are there. And in their interviews, the programming was more about data operations, numerical programming, etc. Not so much about classical data structures and algorithms that is typically asked for CS folks or for software engineering roles. For data scientists, that's not important. But for machine learning engineering roles or software engineer with machine learning roles, that is super important. Especially if you come from a CS background or an IT background. That is super duper important. Because they could say, hey, you studied computer science, so you should know what is a graph traversal. Right? So knowing that is important for machine learning engineering roles, not as much for data scientist roles itself. But for data scientist roles, you certainly have to know the basic data structures, your dictionaries, your lists, your sets. Similarly, some basic binary, you have to know space and time complexity, obviously, right? You have to know basics of recursion, basics of basic dynamic programming. You will not be asked the same questions that are typically asked for software engineers, but basic stuff. Similarly, for example, you have to know KD tree, because KD tree is often used for fast search when you have to do a k nearest neighbor search. Similarly, you have to know basic concepts like locality sensitive hashing. So there are some data structures that are specific to machine learning. Like for example, decision trees, right? Can you implement some functionality of a decision tree from scratch? For that, you have to know basics of trees, right? Similarly, imagine if you have a graph like a social graph. You have to know basic concepts of in degree, out degree, how to come up with features, what is the length of the path. Those basics you should know. So in terms of how much data structures and algorithms you should certainly know the basic data structures, the time and space complexity, and data structures that are relevant in the context of machine learning and deep learning. But for machine learning engineering roles, and they're typically, machine learning engineering roles typically expect you to have a bachelor's degree in computer science or a master's degree in computer science or IT industry background. There you can expect your typical competitive programming type rounds. Typically 1 out of all the rounds will be like that. So highest position one can reach in machine learning engineering path. I've seen vice presidents and senior vice presidents at FANG-like companies who have started their career in the machine learning or data science related fields. So almost like one level below the CEO, I've seen people start their careers in, it was not called data science then, obviously, but I've seen people who come from those math, computational side of things who have reached that one level below CEO. And I'm sure we'll see some CEOs in the future also. Okay, so Akash says the intrusion detection systems, again, depends on the actual problem itself. So for intrusion detection systems, people have started using deep learning. Again, depending on the context. Is your intrusion detection based on some webcam feed? Right? There are a lot of these smart home cameras, right, that can detect if somebody is coming in, it will tag that person. They are mostly using some simple image processing and a little bit of deep learning algorithms for sure. So that has already happened, right? It depends on what sort of intrusion are we talking about. Are we talking about like a video-based intrusion detection system, or like a hacker getting into a server system, right? It depends on the context. But yes, deep learning systems are being used here. Is there a cybersecurity course from Applied Roots? It's not on our horizon right now. It's not on our horizon right now. Okay, cool, folks. I don't know what's happening with the match because I seldom watch cricket. Actually, I didn't know that there was a cricket match today till the time some of my teammates called me up at 6 and said, "Hey, Varma, there is a cricket match. Do you want to postpone it?" I said, "Okay, we announced it, so let's go ahead with it." So cool. Thanks a lot. I've seen phenomenal participation. Thank you very much for participating. Again, please understand that since this is a public live session, it may not be possible for us to answer all questions. So feel free to email us. You can go to Applied AI course. Look at our email address, team@appliedaicourse.com. Please email us. We'll try to answer as many questions as possible. Once again, thank you very much. Stay safe. And I don't know what's happening with the match, but enjoy the match with your friends and family. Thank you very much.